Welcome back everyone. In the last lecture we had seen how does the differential equation corresponding to an LTI system look like. Today we will see how can we use this differential equation to get to a point where we can find out the relationship between the input and the output of the system. This is the operator that I was talking about in my previous lectures. And to get to that, as told in the last lecture itself, we will have to learn about Laplace transform. This lecture will be a very brief introduction to Laplace transform. You can get materials on Laplace transform in any book on signals and systems. However, in this course, I will not be going into details of how to derive the formulas for Laplace transform, properties for Laplace transform. I would urge you to pick those things up from any book on signals and systems that you like. Let us get going. So, what is Laplace transform? So, Laplace transform is a transform that helps you to simplify this differential equation into an algebraic equation. It will help you to find out the relationship between the input and the output with a simple algebraic equation. So, how do we define Laplace transform? If you are given a function ft, the unilateral Laplace transform fs of the function ft is defined in this way. Why I am using the word unilateral? Because there is a version of Laplace transform where the integration goes from minus infinity to infinity f of t e to the power of minus st dt. This we are not dealing with in this course because we have restricted ourselves to t greater than or equal to 0, because these are LTI systems. Even if t is less than 0, we can shift the system and make the time start from t equal to 0. So, we do not need the bilateral Laplace transform. So, we are happy with the unilateral Laplace transform itself. Now, here is the expression for Laplace transform. This should look familiar to people who are already or who have already studied signals and systems, because this is nothing but it looks similar to a formula of this form. And what was this formula? If you remember, this was the Fourier transform of a function or of a signal, right? The only difference now is in place of j omega we have a s here, okay? This becomes an s here and this becomes an s here, that is it, okay? And what is s? S is actually sigma plus j omega. So, in Fourier transform we were only taking j omega, pure imaginary part. Here s is sigma plus j omega. S is a complex number, okay? So, in Fourier transform j omega was corresponding to frequency. Here also sigma plus j omega is frequency, but this is complex frequency because there is a sigma also, okay? Remember this physical interpretation. So, if someone asks what is s? So, s is nothing but complex frequency. So, s is complex number sigma plus j omega, okay. Coming back to the Laplace transform. So, this is the transform. Basically, it is almost like a formula which takes a, it is a formula which basically takes a signal, a function, and then you do this integration, you will get a function in s. Let us try to find out the Laplace transform of this function e to the power of at t greater than or equal to 0. A is a scalar, okay. So, a is a scalar means a is some real number here, and let us try to find out the Laplace transform for this. So, if we directly blindly follow the formula, in place of f t we will write e to the power of a t, and so this will become e to the power of minus s minus a whole t dt, and then we have e to the power of minus s minus a whole t by minus of s minus a, and we have to evaluate from minus infinity from 0 to infinity. Now, the question is, when I put infinity here, will it go to 0? Well, it will go to 0 only if the power, the power of e to the power, the exponent here is a negative number, right? It has to be negative, then only it will go to 0. If it is positive, that means it will be blowing up, right? So, that means this s minus a here, see the s minus a here should be, this should not have been this. So, here real part of s minus a should be greater than 0, right? Why? Because you see, for this s minus a whole t to be negative, so that means what? S is sigma plus j omega, right, minus a. So we want that sigma minus a plus j omega. So if you have to do e to the power of minus of this whole t, this is nothing but e to the power of minus sigma minus a whole t into e to the power of minus j omega t. Now see, this does not blow up, this is a sinusoidal signal. This is the term which may blow up if this sigma minus a is greater than 0, then this will not blow up, right, because as t tends to infinity, this will become 0. So if you draw the function as t changes, e to the power of minus sigma minus a, if you draw the function, it will go down to 0 if this sigma minus a term here is a positive number, and that is what is being written here. So for this integration to make sense, this must be satisfied. This is what is known as region of convergence of the Laplace transform, but we are not going to go into details of region of convergence. Only thing is that you should keep in mind that this Laplace transform is not always valid, it is only valid if real part of s minus a is greater than 0. Okay. So suppose this is valid, real part of s minus a is greater than 0, then you can go ahead and put in the value of infinity here and the value of 0 in place of t. This is what you will get, and finally you end up with 1 by s minus a. So what we are getting is, if function is e to the power of a t, t greater than equal to 0, then f of s is equal to 1 by s minus a. Of course, we also have to write that the ROC here is s minus a greater than 0. But forget about it for the time being, because in this course we will not be dealing with the ROC part much. But if you go into more details, more deep mathematical, if you want more mathematical rigor in your derivations, you will have to look into all those things. As in the beginning of this course itself, I have said that in some cases I will have to compromise on the mathematical rigor, because I want to give you what the concepts are in general. But if you want mathematical rigor, pick up a book and then try to read about Laplace transform and ROCs. It is very interesting, you should read it up. Okay, great. Now what about if it is a unit step function? A unit step function is a function of this form, where the magnitude is 1 for t greater than equal to 0, and for t less than 0 the magnitude is 0. So let us try to find out the Laplace transform of this signal or this function. So what will be the Laplace function? Laplace transform, again similarly in place of f t you will write 1 from 0 to infinity, you do the integration, put it back. So in this case, if you want to find out the ROC, of course in this case the ROC would be this. So in this case, Laplace transform of the unit step is 1 by s. What is the Laplace transform of e to the power of at unit step then? We have already found out e to the power of at is Laplace transform. Let me go back. E to the power of at for t greater than equal to 0 is 1 by s minus a. Then what is this e to the power of at u step t? This is also same, right? The meaning of this statement and the meaning of this statement is the same, right? These and these are the same thing. So we have already found out. So basically what is that? If you do not want to write the signal like this, you can always multiply with it a unit step function, which means that the function for t less than 0 will be 0. For t greater than 0, it is e to the power of at, because unit step for t greater than equal to 0 is 1. 1 multiplied by e to the power of at is 1. So this is a shorter way of writing down the same thing. Okay. So we know that the Laplace transform of this will be 1 by s minus a. Then what will be the Laplace transform of e to the power of j omega t u step? That would be 1 by s minus j omega. What will be the Laplace transform of sin omega t u step? See, I am giving these examples because these are the ones which we will be using quite often in this course. There are a lot of other functions I could have chosen, but I am giving you only specifically these examples because these will be required in this course, and that is why I am trying to give you these specific examples. So what is Laplace transform of sin omega t u step? So that is nothing but integration from 0 to infinity sin omega t e to the power of minus st, right? u step is not required because the function is from 0 to infinity anyways. Now, what is sin omega t? We know that sin omega t can be written like this, 1 by 2 j e to the power of j omega t minus e to the power of minus j omega t, and then we have e to the power of minus s t dt. I hope you know these formulas already. That sin omega t can be written like this. If not, please look it up. Okay. So, then you can do the integration. Again, what is this? This is nothing but Laplace transform of e to the power of j omega t, and this expression is nothing but Laplace transform of e to the power of minus j omega t. I do not even have to do the calculations. I know what the solution is, right? Because this would be nothing but, for this case it will be 1 by s minus j omega, and for this case it will be 1 by s plus j omega, and if you just complete this, it will come out to be omega by s square plus omega square. What I want you all to do is find out the Laplace transform of cos omega t u step t. In that case, we will find it to be s by s square plus omega square. Now, there are lot of properties of Laplace transform that will be needed in this course. As I have already said, I am not going into the proof of these transforms. Please look it up. It is straightforward. The proofs are actually straightforward. You can directly use the formula of Laplace transform and go ahead. You just start from the left hand side and you will reach the right hand side. Okay, try to do it on your own. If not, books are there. You can always find those in the books that has been prescribed or in any other signals and systems book. Now, what are the important properties here? Just let us look at those. First of all, this is like a superposition property. If you have Laplace transform of alpha 1, which is a constant, plus, multiplied by f1 plus alpha 2 f2, then these constants can be taken out, and then you have Laplace transform of f1. We are assuming that the Laplace transform of f1 is capital F1s. So, you will get something like this. So, the constants can be taken out from the Laplace transform, which is obvious, right, because these are integrations, right. From integrations we can always take out constants out of the integration, because they are not dependent on the variable with respect to which you are integrating. Then we have, this is a very important property. See, Laplace transform of e to the power of at f1 t is f1 s minus a. Okay. So, now if I use this property blindfolded, if you want to use it, see what will be the Laplace transform of sine of omega t. So, we know that the Laplace transform of sine of omega t is omega by s square plus omega square. So, in that case, what will be the Laplace transform of this? It will be omega by s square plus omega square, but you see s is getting replaced by s minus a. So, this becomes s minus a whole square plus omega square. If this was minus here, then this would have become plus here. Okay, this is a very essential property. So, this will be required for us a lot. Then comes the property, another important property. What will be the Laplace transform of derivative of a function? If the Laplace transform of a function is equal to f of f1 of s, say, then what will be the Laplace transform of the derivative of that function? The derivative of that function will be given by s multiplied by f1 s minus f1 at the 0th instant, the value of the function at the 0th instant. Now, if it turns out that the function itself is only is non-zero only when t greater than equal to 0 and 0 for t less than equal to 0, then of course, this will go to 0 then. Okay. So, in that case, you can think of it like, if there is a Laplace transform and if you multiply it with s, it is almost like doing derivative of it, of the time domain counterpart of that Laplace transform. I hope you understand it. So, basically, suppose there is f of s, okay, and this is the Laplace transform of f of t actually. Okay. This is what it is. So, if I say s of f of s, you should think, oh, s multiplied by f of s, that means then the actual signal must be this with the assumption that this is equal to 0. That is what it is. Okay. I mean, this will be very important for us, because this will be required for us when we talk about controllers and all. Okay. Next comes integration. So, for differentiation, it was s multiplied by fs. So, if f1 is the function, integration of 0 to t Laplace transform will be f1 by s. Property 5 and 6 are very important property. This is called the initial value theorem and this is called the final value theorem. And notice that in these two properties, what is happening is we are linking the value of the function. F of 1 t is a function, right? It changes with time. So, what is the value of this function at 0? So, what is the value of this function of 0 can directly be found out from the Laplace transform of that function, that will be limit of s tending to infinity s of f1s. This is called initial value theorem, because I can find out the initial value of the function. This is called the final value theorem, where I can find out what is the final value of the function by just doing limit of s tending to 0 s of fs. However, there are certain conditions that are to be met, and we will talk about that soon. And the last property, which is a very important property, you will see soon why this is important, okay, is called the Laplace transform of convolution of two functions. Convolution is also like a operation that can be done on functions, okay, and the operation is defined in this way. Two functions are convolved with each other, means that it is the integration of the two functions where f1 tau and f2 t minus tau d tau. Okay. So, this is the definition of convolution in the time domain, but you see, if two functions are convolved in the time domain, you do a Laplace transform of those two convolved function, that is basically just multiplication in the Laplace domain. We call it the Laplace domain, right? So this becomes easy, right? So that means if two functions are convolving, that becomes so simple in Laplace domain. It is just multiplication of the Laplace transforms. Okay, this is a very important property, we will need it. And the other important property is that, see, from here we got Laplace transform of d dt of f1. The derivative of the function is s of f1s minus f1 0, or the function value at 0. Remember, this is in Laplace domain, this function is in time domain. Okay. Now, what about higher derivatives? So, in higher derivatives, there is a chain of this form. Okay. So, this is the chain rule of Laplace transform of derivative of a function, and this will be useful for us. Now, I go back to the initial value theorem once, and I will tell you what are the things that you have to look for before applying the initial value theorem. See, the initial value theorem, which means the theorem which will give you what is the initial value of the function, can be applied, can be found out, or can be applied on, or this formula which relates the time domain initial value to the Laplace transform. This formula does not apply to rational functions f1s in which the order of the numerator polynomial is greater than or equal to the denominator polynomial. If this function's numerator's order or numerator's degree is greater than or equal to the denominator's degree, then you cannot allow this, you cannot use this formula. Then you might have to directly look at the function and find out the initial value. This formula is not valid then. Very important point, people do make mistakes in it. They think that okay, I can directly use the initial value theorem, but there is a very important note there to keep in mind, that it is not applicable always. This formula is not applicable always. So, you have to look at f1s, and it has to be strictly proper. Strictly proper means the denominator's degree must be strictly higher than the numerator's degree for this to be applied. And the second one, which is the final value theorem, the final value theorem applies to rational functions f1s in which the roots of the denominator are in the left half of the s plane with at most a single pole at s equal to 0. So, this is, see, remember, these are like numerator by denominator, numerator by denominator. Numerator is a polynomial, denominator is a polynomial. Now, if the denominator is a polynomial, it will have roots. So, the roots can be anywhere on the complex plane. If the roots of the denominator are on the left half of the complex plane, what do you mean by left half of the complex plane? The real part of the roots are negative with at most one pole at s equal to 0. So, this something like this is allowed. This is allowed because the pole is, see, the roots of the denominator here is at -1 and 0. So, -1 is anyways on the left hand side, and there is only one root on the imaginary axis, then it is okay, or at s equal to 0. However, this is not allowed. This is not allowed because there are two roots on the origin. Okay, this is not allowed because there is one of the roots is on the right hand side. Okay, so these are not allowed. So, as a whole, when is the final value theorem valid? If the roots of the denominator are on the left half plane, if at the origin there is only single pole or single root. It is not valid if the roots are on the imaginary axis or on the right half of the complex plane. Now how does all these things help us? You see, all these things help us in finding out the operator of the system. So let me just quickly go ahead and tell you how do you find out the operator of the system. Remember, this was the differential equation corresponding to the LTI system. The coefficients are constants here. This is a nice looking differential equation. M is less than equal to n here, so that it becomes causal. Great. Now we will assume, this is a very important assumption. The assumption is that the initial conditions are 0. That means y of 0 minus ddt, yt, 0 minus everything is 0. So y of 0 minus is 0, dy dt, if you do the function that you get, that when evaluated at this is 0. Similarly for u also, these things are 0. So this means that the initial conditions are all 0. With that assumption, you can take the Laplace transform. Okay, you can take the Laplace transform on both sides of this equation. Okay, here we are assuming that the Laplace transform of the input is us and the Laplace transform of the output yt is ys. So then what do we have if we take the Laplace transform? You see, if I take the Laplace transform of entire thing, I can use superposition. This is a constant, I can take it out, right? So then a naught, Laplace transform of yt is ys. A1 I can take out, A1, what is the Laplace transform of dy dt? The Laplace transform of dy dt is s into ys minus y of 0 minus, but y of 0 minus is 0, right? Laplace transform of dy dt is sys minus y of 0 minus, but this is 0 because initial conditions are all 0. Similarly, cyclic property that I had shown, and this is what will be left on the left hand side. Similarly, on the right hand side you will get this. Remember, very importantly, the initial conditions are here 0. So then I can take everything together, ys like this, and in the right hand side we have this. So finally ys by us comes out to be this, which is basically a rational function where there is a numerator polynomial and a denominator polynomial. Okay, and this is what is known as the transfer function of the system. The ratio of Laplace transform of the output, you see, this is the output, to the input, this is the input. Okay, so output and input, ratio of the Laplace transform of the output and input, assuming all initial conditions are 0, is called transfer function of a system. Okay, and why is this important? You see, if ys by us equal to gs, then output is nothing but gs multiplied by us, right? See, remember, we were trying to find out the operator that links the input and the output. So it turns out, instead of linking the input and the output in the time domain, we can take the Laplace transform of these two signals, and the operator is gs here, which means y of s is nothing but gs multiplied by us. A straightforward algebraic equation. Great, we found out the operator. So we have found out the operator that links the input and the output. Next what? Next, let's see how to use this transfer function to find out the response or the output of the system, and that we will do in the next lecture. Thank you.